Hi everyone, myself Ayush Tripathi, mentor at GeeksforGeeks, and I welcome you all to this post-analysis video of last weekly contest 188. So starting with the first problem, good array. In this problem, you are given an array ARR of non-negative integers, and an array is called good if its length n is even, and you can divide the array into n by 2 pairs such that bitwise XOR of each pair is equals to given integer k, and we need to find the minimum number of integers need to be added to make ARR good. So let's just discuss this first sample input. So here the initial length of the array is 3 and the value of k is also 3. So let's call this as array A, and its initial length is 3 and we have 3 elements 1, 2 and 3. And the value of k is equals to 3. So what I can do, I can form this pair of these two elements, because 1 XOR 2 is equals to 3, or I can say it is equals to k. Now for this 3 I will add one element. I will add 0 here, and now XOR of these two elements 3 and 0, it is equals to 3. So 3 XOR 0, which is equals to 3. Cool. And here in this case my answer is equals to 1, as I have added one integer to make this array A as good. Now for every element, to solve this problem, the idea here is to apply a greedy logic. For every element of array A, I will try to find the pair which exists in this array A, and if it does not exist, then I need to add one element to make the XOR value is equals to k. So let's say the element here is A of I. So for this A of I am looking for some elements. Let's call this as y. I am looking for some element y such that their XOR is equals to k. Now if this y exists in array A, so in that case I don't have to add any element. I don't have to add any element. For example, this one. For this one, we are looking for 2, because 1 XOR 2, it is equals to 3. So this 2 exists in array A. So I'm not going to add this element 2 in the array. Otherwise, you will not get the minimum result. So what is the value of y here? So the value of y, it is simply equals to A of I XOR k. And if this value already exists in the array, then do not add any element. Otherwise I need to add one element to pair A of I with some element y. Cool. And this is the complete solution. The time complexity here in this case is order of n, and log of n base 2, because in my implementation I have used a map data structure. You can also use unordered map. In that case the time complexity would be order of n, but in the worst case it can be n square when there is a collision in hash table. So that's why it's better to use a map. In this case, the worst case time complexity would be n log of n base 2, and the extra space is also order of n. So now let me just show you the implementation. So this is the method that you need to complete. Here we have array ARR and integer k. So here I have declared a map, and with this for loop I will hash all the elements and basically increment the frequency of every element x in array ARR. Then my answer is equals to 0. Now if the frequency of x, again iterate over this array ARR, and if the frequency of x is equals to 0, then it simply means I have paired this element with some other element. So this element is fixed now. So that's why I will just simply continue the loop. Otherwise I will decrement its frequency, and then I am going to check whether in my map there exists a occurrence of x XOR k. And otherwise, if it is equals to 0, then I need to add element. Otherwise, I will decrement the frequency of x XOR k. And finally, I will return this answer. There is an edge case. Here, you need to first decrement the frequency of x, because there might be the case when the value of x XOR k is equals to x itself. So let me just give you some example. So let's say the value of k is equals to 3, and array in my array, or instead of saying this as 3, let's say we have 0, and in my array we have two elements, 2 and 5. So here, for this 2, for this element 2, x is equals to 2. What we are looking for? We are looking for 2 XOR k, or I can say 2 XOR 0, which is equals to 2. Now, if you do not delete the occurrence of this 2 from your map, then eventually you will get that we have this 2. We have another occurrence of 2, but this is not true. I need to add I need to I need to add one element for this 2. I need to add 2. Then only the XOR value is equals to 0 or equals to k. Similarly, for this 5, I need to add 5, so that the XOR of these two elements of the pair is equals to k. 5 XOR 5, which is equals to 0. So that's why make sure to first delete the element from the map. So this is the complete explanation for the first problem. So this is the second problem of the contest. Remove segments. In this problem, you are given an array ARR where each element ARR of I is a positive integer, and in one move you can choose a unique value of k, and remove a consecutive segment of the array where all elements are equals to k, and after removal the remaining elements are joined together in the same order. And here you are allowed to use each value of k only once, and we need to check whether it is possible to make array ARR empty. So let's just quickly discuss this first sample input. And basically in this problem, you have to visualize the elements in terms of interval. So let's just quickly map the elements with some interval. And the starting point of the interval will be the first occurrence of the element, and the end point is the last occurrence of the element. So let me just write the indices. So this is index 0, then index 1, index 2, index 3, index 4, and index 5. So the first occurrence of element 1 is at index 0. The last occurrence of element 1 is at index 5. So I can say there is an interval from 0 to 5. From 0 to 5 we have an interval. Now the next element, which is 2, the first occurrence of 2 is at index 1. The last occurrence of 2 is at index 4. So I can say there is an interval from index 1 to index 4. Or basically it is 3, not 4, the last occurrence of 2. So there is an interval from 1 to 3. And the next element, which is 3. So this interval is of length 1, and it starts at index 2 and also ends at index 2. So we have an interval from 2 to 2. Now here I can see we have some interval, but here no two interval intersect each other. So in this case, it is possible to make array A empty, and how we perform the operation. So first I will select the value of k as 3, and and this operation will delete this segment, this interval, and then I will select the value of k as 2. So this operation will delete this interval from 1 to 3, and finally I will select the value of k as 1, and this last operation will delete this interval. So with this set of operation, I can delete this array. I can make this array A empty. So now here I can conclude, if we have a intersecting if we have an intersecting interval, then it is not possible to make array A empty, because in that case we have a deadlock type of condition. Otherwise, it is always possible. Now let me explain you with this example. So this is index 0, then index 1, index 2, index 3, index 4, and index 5. So we have an interval which starts from index 0 and it goes till index 5, because the first occurrence of element 1 is index 0 and the last occurrence of element 1 is index 5. Now the next interval that we have is from 2 to 1 to 3. 1 to 3. The first occurrence of 2 and the last occurrence of 2. So we have an interval from 1 to 2. 1 to 3. And then the first occurrence of element 3 and the last occurrence of element 3. So I can say we have an interval from 2 to 4. Now here we can see these two intervals are intersecting each other. So in this case it is not possible to make this array empty, because to delete all the occurrences of 2 I must have to delete all the occurrences of 3, and to delete all the occurrences of 3 I must have to delete all the occurrences of 2. So this is a kind of a deadlock condition. So that's why it is not possible to make this array empty. And there is an edge case that you might have missed. We might have a we might have some other intervals, and let's say we have another interval which is starts from index 6 and this interval ends at index 7, or let's call this as index 10. And here we might have some other elements. Let's say this is from 7 to 9 and the interval from 8 to 8. So make sure to handle this type of case. Now you know the idea. I just only need to check whether we have a intersecting interval or not, and how we can implement this approach. So there exist multiple methods, and in my implementation I have used a stack data structure. So let me just explain you my approach with the help of a first sample input. So here first I will what I will do, I will store the last occurrence for every element. For example, the last occurrence of 1 is at index 5. So let me just color this. The last occurrence of index 2 is at the last occurrence of index 2 is 3. The last occurrence of index 3 is 3 itself. And after this, I will iterate over the elements. So I will iterate over the elements, and now here I got 1. I got 1. So this is my stack data structure. So here I got 1. So what I will do in my stack data structure, if it is empty, then I will push the last occurrence of index 1. So this simply means I have initiated some interval. So this is my index 0 and the last occurrence of index 1. The last occurrence of element 1 is at index 5. So I will just simply push this 5 in my stack, and this simply means I have initiated one interval. Now let's just move to the next element. The next element is 2, and the first occurrence of 2 is at index 1, and the last occurrence of 2, is at index 3. This is the last occurrence of 2. Now here I can simply conclude that the previous interval and this current interval is not intersecting each other. And how I can check whether it is intersecting or not? So for this thing, you just only need to check with the topmost element of the stack. So here the topmost element of the stack is 5, and the last occurrence of 2 is 3, is at index 3. So this simply means this 5 is greater than 3. And if it was less than 3, what if it was less than 3? So if it was less than 3, let's say we have the first occurrence of 2 at index 1 and the last occurrence of 2 is at index 7. So in this case the last occurrence of 2, which is 7, and it is greater than 5. The 7 is greater than 5. So in this case we have an intersecting segment. So I will just simply return false. It is not possible to make this array empty. Otherwise I will just simply add this element. So otherwise I will just simply add the last occurrence of element 2 in my stack at the top. So here I will just simply add this 3. So this simply means this is my current interval from 1 to 3. Now the next element, which is a 3, and the first occurrence of 3 is at index 2, and the last occurrence of 3 is at index 2 itself, and this 2 is less than the topmost element of the stack. The topmost element of the stack is 3. So this is a happy case. This is an happy case. And once you reach to some index I, such that the topmost element of the stack is less than or equals to this index I. So this simply means now you have reached to the last occurrence of some element. So I will just simply remove this 2. I will just simply remove this remove the topmost element. So for this element 3, I will add 2, and then I will just simply remove this 2, because currently we are at index 2. Currently we are at index 2. So before moving to the next element, I will remove this 2, because some interval ends at here. Now I will move to the next element, which is the last occurrence of 2, and the last occurrence of 2. So I will remove this 3 from here. Then I will move to the next element, and the last occurrence of this one is 5. So this is in a happy case. Here we are not violating any condition. The last occurrence of this one is 5, and at the top of the stack we have 5. So this is less than or equals to the topmost element of the stack. So this is an happy case. So I do not claim anything. Now let's just move to the next element, and then finally I will move to the next element, which is index 5. And again you can see this 5 is less than or equals to the topmost element. And before moving to the next element, I will remove this 5. So in this way we can solve this problem in a linear time order of n, and in a linear space complexity. So now let me just show you the implementation. So here I have used the map data structure. So in this case, the time complexity would be n log of n base 2. But in case if you use unordered map, then it is order of n. So first I will store the last occurrence of every element ARR of I, and then this is my stack. And here in this stack, if the last occurrence of element at index 0 is greater than 0, this simply means if the first interval has size greater than 1, then I will just simply add the end point of the interval in my stack. That is last occurrence of this first element, and then I iterate over the remaining indices from 1 to n minus 1, and simply I'm checking if the topmost element of the stack is less than the last occurrence of the current element. This simply means we have a intersecting segment, so simply return false. Otherwise I will add this, and this is a pruning case where I will remove all the element from the stack, all the indices from the stack whose value is less than or equals to I. So basically these intervals are no longer existing. So that's why I'm removing these intervals from the stack. And finally I will return true. Cool. So the time complexity is n log of n base 2 in case if you use a map data structure, and it is order of n in case if you use unordered map. So yeah, this is the complete solution for the second problem. So coming to the third problem of the contest, maximum average subsequence. In this problem, you have been given an integer array ARR, and you have to select a subsequence from the array in such a way that from every pair of adjacent element, at least one element is taken into the subsequence. And the average of the subsequence is maximum. And you need to return that maximum average. And this average may be a decimal number. So the answer will be considered correct if the relative error between the user output and the expected output does not exceed 10 power minus 5. Basically 5 digits after the decimal point. So for this first sample input, from these two adjacent elements, I will select 4 to get the maximum average, which is 4 here. Now let's see how we can solve this problem. So the idea here is to apply the binary search, because if it is possible to achieve some average, then it is also possible to achieve average lesser than that number. So let me give you some example. Let's say we have array A of 3 elements, 5, 4 and 6. So here in this case, the average is simply equals to sum of all the elements, which is 5 plus 4 plus 6, and divided by the number of elements, which is 3. So in this case, the average is equals to 5. 15 divided by 3, 5. Cool. So my claim is that it is possible to achieve average lesser than the 5, lesser than this 5. Because if the average is 5, then this simply means the sum of numbers which has been considered in the sequence, in the subsequence, is having value greater than or equals to this 3 into 5, this 15, greater than or equals to 15. So if I delete some element, then definitely my average will either reduce or it will remain same. So currently my average is 5. Now what if, how we can achieve the average lesser than 5? So just simply delete this element. Delete this element 6, the maximum element of the subsequence. If I delete this 6, now the new average is simply equals to 5 plus 4 and divided by 2, because the number of elements is now equals to 2. So here in this case, the average is 4.5. It is possible to achieve some average which is less than this 5, 4.5. Now how we can further reduce it? So to reduce this average further, what I can do, I can delete this 5. I can delete this 5. Now the new average is equals to 4. So my claim is that just simply apply a binary search. Just simply apply a binary search. If it is possible to have the average as mid, let's say my check function of binary search is returning true for this, then it is also possible to have the average lesser than mid. That is a mid minus some constant. Let's call this as a C1. Then a mid minus some constant, let's call this as a C2, and so on. So the check function of a binary search will also return true for mid minus some constant C2, also returns true for mid minus some constant C1. And if it is not possible to have the average as a mid plus 1, then it is also not possible to have average greater than a mid plus 1 or equals to mid plus 1. So for example, here I'm not going to write all the real numbers between mid and mid plus 1, but here I'm just only simply writing the integer. So basically, or yeah, so basically the function will return false for mid plus 1, and if it is returning false for mid plus 1, then it will again return false for mid plus 2, or basically any real number greater than mid, that is midpoint 2, midpoint 002, any real number greater than mid, the function will return false. So here we have a monotonic predicate nature of the monotonic predicate nature. So I can just simply apply a binary search and apply a binary search to find the maximum value for which the function is returning true, the maximum average. Now I have fixed the average. But before writing the logic, how we can check that whether it is possible to have some particular average or not, let's just first find the range of binary search. So the value of low and the value of high. So here in this case, what could be the minimum average possible? The minimum average possible is simply the minimum element of the array. So the value of low is simply equals to the minimum element of the array, 0 to n minus 1, minimum value of a of I. And the value of high, the maximum average, it is simply equals to the maximum element of the array. So 0 to n minus 1, and the maximum of a of I. Now, how many time I will apply the binary search? Because in binary search, we generally write the condition while low is less than or equals to high. So we write this condition when my answer is integer, when my answer is a whole number. But this time we have to our average can be a decimal number, and this decimal number should not exceed the absolute error. So this decimal number must be of 5 digits after the decimal point, that is 10 power minus 5. After the decimal point, the expected output and the user output must matches all the 5 digits after the decimal point. So this simply means we must have all the digits correct after the decimal point, or I can say my answer divided by 10 power 5. So how many time I will apply the this binary search logic? In a trivial binary search solution, we always write this condition while low is less than or equals to high. But this is the case when my answer is a whole number. But this time we have a real number, decimal number. So in this case, how we can write the solution? So my claim is that just simply apply the binary search for 80 times. And why it is 80 times? Let's just analyze the constraint. So here the value of element can be up to 10 power 5. So a of I can be up to 10 power 5. So in this case, the initial difference is a 10 at max 10 power 5 minus 1. So let's just consider this as a 10 power 5. So the initial difference between low and high is exactly equals to 10 power 5 minus 1 in the worst case. But let's just consider this as 10 power 5 as the upper limit. So this is log of 10 power 5, log of 10 power 5 and base 2. Cool. And then I need to take 5 digits after the decimal point. So just simply multiply this by 5, and basically let's just find this value. Then I will just simply decide how many time I will apply a binary search. So this is simply equals to 5 multiplied by log of 10 base 2. So log of 10 base 2 is greater than 3 but less than 4. So let's just consider this as the upper limit of 4. So this is simply equals to 5 multiplied by 4. So this is equals to 20. This is equals to 20. And now in the worst case, in the 20 iteration, you will reach to some particular integer. You will reach to some particular whole number. And now I need to find the digits. Let's say this is my answer, or let's say this is 4. Now I need to calculate the answer after the decimal places, and up to 5 digits. So for this thing, it is enough to multiply this 20 by 4, or even you can multiply with any number greater than 4, because log of 10 base 2, this is greater than 3 but less than 4. So let's just consider this as 4. So how many time I will apply the binary search? This is simply 20 multiplied by 4. This is enough. 80 times. 80 times I will apply the binary search. So let me just show you the implementation, and then after I will discuss the rest of the approach. So implementation for this binary search template. So this is the method that you need to complete with the vector ARR. So here I will first initialize my low with the minimum element of the array, and high with the maximum element of the array. Then initializing answer with 0, and then apply binary search at least 80 times just to be on the safer side. And you can also write this 100 or basically any integer greater than 80. And then here I am finding mid, and if it is possible to have average as this mid, then I will update low. So low is equals to mid. Otherwise I will update high with mid, high as mid. Cool. Now let's just discuss the logic for this check function. So now I have fixed my average. I have fixed my average. So my average is equals to this mid. Now I need to check if it is possible to select at least one element from every adjacent pair such that their average is greater than or equals to this mid. So let me just write some sequence here. Let's say we have array, or let's say we have selected k elements. So let's say we have selected k elements, and these key elements is a part of this array A. So let's say we have A1 and then the next element A2. So plus A2. Do not get confused. I will not select in this way. Do not consider this A1, A2, these numbers, because okay, but you know the logic. So plus A3, because I just only have to add key elements, some k elements, and one element from every adjacent pair. So A2, A1 plus A2 plus A3 plus A4, and yeah, this could be some random indices, and plus A of k elements I have selected. So what will be their average? So I want their average to be equals to mid, and this is the formula of average: sum of elements divided by the number of elements. So here I have assumed that I have selected k elements. Now let's just further solve this formula, further simplify this. So A1 plus A2 plus A3 and plus A4 up to plus A of k. This is simply equals to, this is simply greater than or equals to this mid, greater than or equals to this mid. If it is possible, then I will return true, and so I can simply say mid multiplied by k. Now what does this mean, mid multiplied by k? This simply means adding mid k times. So I can also write in this way: mid plus mid plus mid, and basically k times I will add mid. So I can say k into mid. Now if I move all these terms to the left hand side, then I can simply say this is A1 minus mid, the average that you have fixed, plus A2 A2 minus mid, A2 minus mid, and plus A3 minus mid, and so on up to plus A of k minus mid, and this value must be greater than or equals to 0. So from the initial array, I will subtract this fixed average from every element. So this is my initial array. So let's say this is A1, then A2, then A3, then A4, A5, and up to A of n. And from here I will create a array v. I will create array v, and the value of array v of I, this is simply equals to A of I minus mid, from the value of the element minus the average that you have fixed. So minus mid. This is my array v. So let me write in this way. So minus mid, and minus mid, and so on, minus mid from all the elements. Now from these elements of array B, I need to select some elements. I need to select some elements such that at least one element from every adjacent pair is being selected, and their sum is greater than or equals to 0. So let's say I have selected this A1, then I have selected this A3, then I have selected A4, and basically at least one element from every adjacent pair. And if it is possible to have their sum greater than or equals to 0, then it is possible to achieve this fixed mid, this fixed average, this fixed average. Cool. And this is a very standard problem of the dynamic programming. This is a very standard problem of a dynamic programming. So let's just define the state. So now we know we have array V, and V of I is equals to A of I minus mid. So let's call this as a V1, then V2, then V3, then V4, and some element V of I, then V of I plus 1, I plus 2, and up to V of n. V of n. So okay, let me write according to zero based indexing. So index 0, then index 1, index 2, index 3, then index n minus 1. So let's create a DP array of size n plus 1, and plus 1 just to handle the base case, and of size 2. So here dp of I comma 0, dp of I comma 0 will simply store the maximum sum possible from the subarray v of I to v of n minus 1 if we not select, if we do not select this element which is at index I. If we do not select index I, and similarly dp of I comma 1, this will simply store the maximum sum possible from the subarray v of I to v of n minus 1 if we select index I. If we select index I. So now what will be the transition? But yeah, let's just write the transition. So dp of I 0, this is simply equals to dp of I plus 1 and comma 1. So from every adjacent pair, I must have to select one element. So if I decided to do not select the element at index I, then I must have to pick the element which is at index I plus 1. So that's why dp of I plus 1 comma 1. And what is the value of dp of I comma 1? So if I decided to pick the element at index I, so now I have two options. Either pick the element which is at index I plus 1, or do not pick the element which is at index I plus 1. So I will select the maximum of these two possibility. So v of I, since I have picked the element, so I will get the value corresponding to it, and plus maximum of dp of I plus 1 and 0 comma dp of I plus 1 and 1. And what will be my base case? So my base case is simply dp of n comma 0 is equals to dp of n comma 1, and it is equals to 0, because from empty array it is only possible to form an average whose value is equals to 0. So this is my base case. This is my base case. Now what will be my answer? If it is possible to have a sum greater than or equals to 0 from this entire array, then I will return true. So for index 0, I have two possibility. Either I will select this, or I do not select this. So whichever will give me the result, I will choose that path. So return true. So I will simply return true if maximum of dp of 0 comma 0 when I do not select index 0, comma dp of 0 comma 1 if I select index 0, and if its maximum is greater than or equals to 0, then I will return true. Then I will simply return true. And initially I will initialize all the values to some very small values. So let's say this is a minus 10 power 9, or basically you can also use int min. So this is the complete solution. Now let me just show you the implementation here for this check function. So first I have taken the size of the array, and then I have created array V, and this is my DP array of size n plus 1 cross 2. These two are my base cases. Then I iterate over all the indices from n minus 1 to 0, because for index I must have to know the value of DP of I plus 1. That's why I have iterated from right to left, bigger values of I to the smaller values of I. And yeah, these are the transition. And finally I am checking if DP of maximum of DP of I, DP of 0 comma 0 comma DP of 0 comma 1 is greater than or equals to 0, then I will return true. And finally I will return this answer. Instead of returning this answer, you can also say this as low, because here we are not updating the low. And what will be the time complexity in this case? So the time complexity is 80 multiplied by the size of this array. So 80 multiplied by n. So the time complexity is order of n multiplied by 80. And in the worst case, the size of the array is up to 10 power 4. So this is the feasible time complexity, and it will pass all the test cases. So this is the complete explanation for the third problem. So coming to the final problem of the contest, maximum operation. And this problem was easier as compared to other weekly contest last problem. So let's just quickly discuss how we can solve this. And here it has lot of casework, but the greedy solution will work out here. So you are given an array of a positive integer. Let's call this as ARR, and an integer k. You can pick two distinct indices I and j from this array and remove the element at these indices if at least one of the following condition is satisfied. Either both the integers are same, or their sum is divisible by k. And we need to determine the maximum number of above operation that we can perform. So we can delete two indices I and j if their values are same. So a of I is equals to a of j, or their sum is divisible by k. A of I plus a of j, and this mod with k is equals to 0. So my claim is that it's always optimal to perform the second operation and then perform the first operation. So we'll give the priority to this second operation, and then I will perform the first operation. So let me just give you some example. Let's say the value of k is equals to 7, and basically this is the first sample input. And array A, we have 4, 10, then let's say again 4 and 17. So in this case, if you perform the first type of operation, then you will select these two indices and delete their values. Now we are left with the 10 and 17, and 10 plus 17 and their sum, which is equals to 27, and 27 mod 7 not equals to 0. So in this case, you will claim that answer is equals to 1. We can perform operation for only one time, but this is not true. If I perform the second type of operation first, then I will get some better answer. So just simply pair this 10 and 4 and this 4 and 17. So here in this case, 4 plus 10, which is equals to 14, and 14 mod 7, which is equals to 0. So this is the first operation that I have performed, and the second operation on the remaining elements, 4 plus 17, which is equals to 21, and 21 mod 7, this is equals to 0. So this is the better answer. I can perform the operation two times. So this is the example for my claim that it's always beneficial to apply the second type of operation. Now let's just quickly draw some casework, and I will explain you the approach with some example. So let me just draw some array. I will filter out the element based on their frequency into two map data structure, odd and even. So let's say the value of k is equals to 4, and in my array A, let's say I have these elements. So I have three occurrences of element 3, Then let's say I have two occurrences of element 2, and let's say I have one occurrence of two occurrence of element 1 and one occurrence of element 5, and let's say I have two occurrence of element 6. So here what I will do, I will first give the priority to the second type of operation. So here I can filter out these elements based on their frequency. So let's just create a two map. I will create a two map, odd and even. So map, and the key is integer, and the value will also be integer. Basically, key is the value, and value of it, value at the index, and the another one is the frequency. So let's call one map as odd and another map as even. So here in this even map, I will store the count of elements whose frequency is even. So for this three, we have three occurrences of 3. So in my odd map, I will just simply store this 3 mod 4, and basically I will take a mod with 4, because eventually I need to know the additive modulo inverse. I am looking for the additive modulo inverse. So for example, let's just take a mod with 4. So mod with 4. Now 3 mod 4, which is equals to 3, then all the 3, then we have a 2, 2, and 1 and 1, and then we have a 5 mod 4, which is equals to again 1. Then we have a 6 mod 4, which is equals to 2 and 2. Cool. So here in my odd map, I will store the count of elements whose frequency is odd. So I will store 1 for each element whose frequency is odd under their modulus with the k. So first we have 3. So in my even map, this is my even map, and even of 3, I will store 2 here. That is the number of elements which has even frequencies. So we have a 2 pair, because in my answer I can just simply add this 2 by 2. That is, I can form one pair and apply the operation of type 1. But my first priority is to apply the operation of type 2, and at the same time it has a odd frequency, so I will store 1 corresponding to the key 3. So odd of 3, this is simply equals to 1. Cool. Now let's just move to the next element, which is 2. So even of 2, and store the count of elements, which is 2. So I'm storing all the even count here and odd count here. One odd count here if it has. Then we have 1. So I have 3 occurrences of 1 after taking the mod with a k, because eventually we are looking for this mod with k. So here in even of 1, I will store 2, because I can perform the operation on these two pairs, and then in odd of 1, I will store 1. Then the next element, which is a 6. The next element, which is 6. So even of 6, and basically after taking a mod with 4, you will get a 2. So let's just increment this value. So previously it was 2, now it has changed to 4. That is, we have 4 elements whose mod with 4 is equals to 2. Now let's just find the answer after getting the values in these two map. So initially my answer is equals to 0. So now I will iterate over this odd map, because for this even map I can easily find the answer. Just simply divide all the values by 2 and add it in your answer. But this odd map which is creating a problem, because I need to fix these elements. So first we have some elements whose modulus is equals to 3. So now what we are looking for? So for this 3, for every remainder, I'm looking for its complement, or I can say additive modulo inverse. So I am looking for its complement, and its complement value is simply equals to k minus this remainder, the complement of remainder. k minus remainder. For example, let's say your remainder is 3 and the value of k is equals to 4. So 3, then I am looking for 4 minus 3, which is equals to 1. And if I add these two values, then I will get 4. And we all know 4 mod 4, which is it is equals to 0. So basically here I can apply the operation of type 2. That is sum of a of I and a of j mod k is equals to 0. So that's why we are looking for complement, and the value of complement is simply equals to k minus this remainder. Cool. And so here the value of remainder is equals to 3. Value of remainder is equals to 3. And what is the value of complement? So the value of complement is equals to 1. 4 minus 3, which is equals to 1. So that is, I will select one element from here, and one element from this from here, and another element whose modulus value is equals to 1, and will apply the operation of type 2 because their sum is divisible by k. So let's say these values. Let's say these values 3 and 5, and you know which one is better. It's better to use this 5. It has a remainder 1 instead of this one, because these values are forming a pair. So it's better to use this 5. Cool. Now I have fixed this. Now what? Now the next one, we have 1. Now the next element that we have is 1. So for this 1, remainder is 1. So what we are looking for? The complement value is simply equals to 4 minus remainder, which is equals to 3. For this one, we are looking for 3. For this one, we are looking for 3. So let's just we have some elements, but not in this odd array. First, I will check for this, or first I will check in this odd map, and then I will check in this even map, because after pairing this element, now it has changed to 0. Now for this one, or basically I have paired these two, so now both the elements has changed to 0, because first I will check for odd. So this has changed to 0, and this one has also changed to 0. Now my odd map is empty because all the elements has frequency 0. But there might be the case when you have some other elements. So let me just give you some example. So let's say we have 9 here. So let me just add 9 here. So this 9 and this 9. So here it is 9. So if you take a mod with 4, then it will change to 1. So this simply means the frequency of odd of 1 is equals to 2. One for 5 and another one for 9. So now this is equals to 2. So after pairing 3 and 1, we are left with another occurrence of 1. Now the remainder is 1, and we are looking for 3. So now I will select this 9 and its complement, that is element whose remainder is equals to 3. So we have this 3. So now I will pair these two elements. Now some of you might wondering that if I do not pair these two elements, then also we will have the same answer. But yes, it is true for this test case. But we have some test cases for which your this claim will be fail. So at this point of time, because we have already seen that it's optimal to apply the operation of type 2 first, and then we'll apply the operation of type 1. So my first priority is to relax all the elements of this odd map. So I will map this 9 with 3, with this 3. Cool. So first I will check. I will check in my odd map, but it has already changed to 0. So we do not have any occurrence of element whose modulus is equals to 3. Then I will check in my even map, and in my even map we have element whose remainder is equals to 3. So I will decrement its frequency. So now I will change this one to 1. Cool. And here I have incremented my answer 2 times. One for this one and another one for this current remainder 1. Cool. And now my odd map is empty. So let's just iterate over this even map. And for every remainder and its frequency, just simply add divided by 2 and add this in your answer. So here we have a frequency of 3 as 1. So 1 divided by 2, which is equals to 0. Then 4 divided by 2, which is equals to 2. And then we have 2 divided by 2. Because I know now I cannot pair this 3 with any element. Then we have 2. So I can pair these elements together. I can pair these elements together, and I will pair these elements together. So in this way, my answer is simply equals to, and these one, this one. So in this way, my answer is equals to 2 plus 0 plus 2 and plus 1, which is equals to 5. And this is the maximum answer that we can achieve. So this is the complete explanation for the solution to this last problem. Let me just quickly summarize all the things and all the observation. So my first observation was that it's always optimal to perform the operation of type 2, then perform the operation of type 1. Because if we have both the possibility, then it's better to perform the operation of type 2, because we might get the wrong result if we give the priority to the first operation. And you can check with this example. Then here in my implementation, you might have some different implementation, but as per my implementation, I have filtered out all the elements based on their frequency and declared two map, odd and even. And in this odd map, I will store the count of elements whose remainder is odd. So basically, let's say, for example, let's say we have 3. So here we have a 3 occurrences of this 3. So I will store the 2 occurrences in the even map and 1 occurrence in this odd map. So this simply means I want to fix this. I want to fix this 1 occurrence of 3, because the 2 occurrences I can pair them together and apply the operation of type 1. So then I will apply. Then I will iterate over this odd map first, because as we have already discussed, first give the priority to the second operation, and then after I will apply. I will iterate over this even map and simply add the value corresponding to the key divided by 2. Now let me show you the implementation. So this is I have used unordered map, but it is not a good idea to use the unordered map during the contest. So first I have stored the frequency of all the elements. This is kind of a dummy unordered map. And then these are my odd and even map. Then I iterate over all the elements of this frequency map. And for every element, I know the frequency. So this is the element value, and this is the frequency. So if this frequency is odd, then I will store one occurrence in an odd map and the remaining occurrence in the even map. Then initializing my answer with 0, and while odd map is not empty. So remove the element which is at the beginning, and then this is the remainder corresponding to this key value pair. So then I will delete this from odd map, and if its frequency is equals to, if its value, or you can say frequency, is equals to 0, then erase it from the odd map. Then this is the complement that we are looking for, and if its complement is present in the odd map, then I will select from the odd map. Otherwise I will check in even map. So if it is present in the odd map, then I will decrement it, and if now the value is 0, then remove it from the odd map, and I will increment my answer by 1. Similarly, if it is not present in odd map, but if it is present in even map, then I will choose from a even map and decrement its frequency, and incrementing the answer by 1. Then I iterate over all the elements of all the key value pair of the even map, and simply add value by 2 in your answer, and finally I am returning this answer. Now what will be the time complexity? So the time complexity is linear, order of n. And in case if you use map instead of unordered map, then it would be n log of n base 2. So this is the complete solution for all the 4 problems, and I hope you have learned something new. Make sure to like the video and write your feedbacks in the comment to improve the upcoming problem set and this analysis video. So thank you so much guys for watching this video, and have a good day.